Hello everyone. So far, we know about sequence alignment and statistical significance of sequence alignment. And today we talk about suffix trees and suffix arrays. Before talking about it, let's mention about some common problems that we have in general, not just related to bioinformatics. Like for example, let's assume that we have this string named P, which includes M elements, and we want to know how to find the occurrence of P in a text. So for example, we have a large text, and the size of that is N. Now we are interested in finding this string, and how many times maybe we want to see this string happens inside this big text. So it's like finding a substring from a string. This is a common problem that we are dealing with in computer science. Or given two strings, S1 and S2, now how to find the longest common substring. And previously we talked about even a formula related to finding the longest match, for example. It was somehow related to this one as well. But today, mainly, we will talk about suffixes and how we can construct a suffix tree in order to deal with such problems. Now, why do we need suffix trees, we could ask. And this one especially is good for database design. If you want to design a efficient database, then suffix trees could be very useful. But first, let me tell you about suffixes, and then we will introduce you about suffix trees right after it. So, any string of length m can be generated into m suffixes. So, with the same length of the string that you have, you can have m suffixes for it. For example, let's say this is your string, just 4 elements. Whenever you want to write the exact suffixes, you can start from the last one. The last character is D. Then you include the one on the left side of it. So ST and JST and the whole string. So as much as elements that you have in your first string, you have as much as suffixes. So 4 is the length of this string, so you can have 4 suffixes for it, as you can see. I just showed it with red color so that you see that this is our initial point for degenerating these suffixes. And what do we mean by prefixes? It is actually starting from the first letter instead of the last letter. And for example, S is the prefix of D, as you can see, and D is the suffix of S, and as you can see, we can construct the whole thing like this. These are the general things not related to bioinformatics so far, but suffix trees are the ones that we are using in bioinformatics, which is very useful. So let this string to be starting from 1 to n. It means that the size of it is n. A string of length n over a fixed alphabet. So we know that the elements that it can have are limited anyway. So a suffix tree for S is a tree with n leaves. I will show you also in some drawings that what do we mean by that. And these are these leaves representing n suffixes. And the following properties should hold for whatever suffix tree that you have. Let me show you an example, like something like this. These are nodes or places, nodes, some dots, and you connect them with a edge. So these ones are called arc or edge. Something like that. You are already familiar with what is a tree. But whenever we talk about suffix trees, it has some properties that we should check one by one. And these nodes at the end of it, we call them leaves. Okay, so if I have, for example, 3 of them, it means that my string has 3 elements anyway from the beginning. Okay, so if we have 3 number of elements, for sure we should have 3 number of suffixes. And this one we call root of the tree. This is root. These are the lines which are connecting them are edges. And these ones at the end that we have are representing suffixes, and we call them leaves. Now, what are the properties of suffix tree? Every node other than the leaves have at least 2 children. It means that when I start from the root from the beginning, I should know it should be connected to at least 2 other nodes. When we say children, it means that everything starts from the root, then it has, for example, 2 children. Again, here it should have 2. But the leaves themselves, they are not connected to other nodes after it, right? So these are the endpoints for us, and we call them leaves. And I will show you how it represents suffixes later. So, for example, if I have 8, like if this is a tree, this one is not a tree. Why is that? Because as you can see, this node just contains 1 child. It should have at least 2 children or more. Okay, so this property is important, and we should have it for all suffix trees. Every edge is labeled with a non-empty substring of S. So for each one of these edges, we can have some title, like, for example, if 1 represents to G, 2 is C, then the 3rd one is A. Then I should have, for example, such name for each edge. Like this one is G, this one is CA, and so on. And what I'm saying is that it's not possible that one edge doesn't have any name. It's not possible. So if this is the case, then this is not a suffix tree. Okay, so each edge should be labeled with non-empty substring of S, whatever the letters are, G, C, or only A, or whatever they are. Edges leaving a given node have labels starting with different letters. This is very important. It means that it's not possible to have GA here because they are starting with the same letter. They should have different starting substrings. Like, for example, whenever you have different edges here from the root or any node inside this suffix trees, then you should make sure that the first letter is different from other. So this one can start with any letter rather than G now. Let's say even AC itself that you can have here is okay, but it shouldn't be started with G anymore. Okay, so the first letter is important in the labels. Now let's see this example. Let's say we have this string and we want to show the suffix tree for that. I will also show you how you can construct it yourself later. So from the beginning, you notice that the length of S1 is 6. So you should have 6 number of suffixes, and because of that, you will have 6 number of leaves. Now let's see what it means. For example, here we start with XA. So this is one way to go. A, this one, and C. So when I start from the root, for example, consider the leaf number 6. Then this one is C. That's it. After that, you don't have anything else. And this one, we already showed that this is one suffix of this string. Just compare with this one, and you will see that we are interested to show all of them in the same picture. You see, so that's what we are doing here. We are organizing our string into a suffix tree like that. And you may say, okay, this one is much easier to understand why we are doing this. Because when you have a large string, of course, it gets much complicated to find the substring from it. At least manually, you can do that easily. So for that, such trees can be very helpful. And I would show you also in some examples that how difficult it can be and how easy it can be sometimes for suffix tree comparing to this string. Okay, so for example, what this one means? Here, for example, we start with A, and then after that, this node has two children. So if I choose this root, then I will have A, C out of it, you see? Or if I choose this one, then I will have A, B, X, A, C. You can find all of them inside this string as a suffix. And I will also show you later how we can find the patterns. How to find a pattern in the string? For example, how can we check whether ABA pattern can be found in S1? So as we said, for a small string, small size of string, it's very easy to even observe it right away. But for a large one, and when the size of substring it even gets larger, it's not that easy. So in order to find it, we can use such suffix trees, and I will show you how. For finding any pattern in the string, we should know that the pattern should be a prefix of at least a suffix. So you already know a prefix, and you know about the suffix. So I will show you what it means exactly in the picture, because when we are just talking about it like this, it may get confusing. That is, we should start from the root to find it. So whenever you want to find everything, as I showed you in the previous example, you should start from the root in order to find different suffixes. Note that for some string, it is not possible to construct a suffix tree. For example, AA, very small string, and we cannot have a suffix tree for that. But why is that? For example, this is my root, then I just start with labeling this one with A. And what should I do next? I cannot have another one to show with another A, because we should check that does it have any contradiction with tree properties or not. So that could be a problem. Even if I continue this one, and I will have another A here to represent AA, that's also another problem, because each node before the leaf should have at least two children. This one has only one child, you see? So that's problematic. And I cannot have also empty string, so that I can again choose this one, for example, for A. It's not possible. So whatever I do, I cannot have a suffix tree for this one. To solve this problem, we can do this. By adding a symbol at the end of your string, we should make sure this symbol doesn't exist throughout the string. For example, I use $, and I add it at the end of my tree. So at the end of my string, so that I can now have a suffix tree. Let's see how we can do that. Like, for example, I can have $, here, and this is one leaf. I should have three of them, right? At the end, I know that I will have three leaves at the end of it. So one of them could be now. What can I say now about $? We showed that one. What are my other choices? I should have $, and AA $. So from here, I can say I start with A, and from here I can go to another A and $. So I constructed already AA, $, and for $, I can continue this one, and I will have AA dollar as well. But it could be a problem here. Let's see. For example, let's say we have dollar here. What would be the problem if I construct it like this? Can you tell me? The problem is that this one should have 2 children. So that could be problematic. So how can I solve this problem now? So let me show you here. I don't have that much space. So we will have dollar here. I want to construct it the way that I will have double, not having, for example, this problem that each node should have 2 children. And you see, it's not even easy sometimes to construct only for 3 letters a tree. There's not enough space. Maybe it's better I show you the more complicated version. So what you understood that for AA, we cannot have a suffix tree. I added $1 here so that I will have a suffix tree at the end, and I will show you even for more complicated example that how can I have a suffix tree for that. And as you understood, even for 3 letters, I'm sure that for this one we can easily have a suffix tree, but even for this one it's not easy to do that because you see we will have some problems, and I will show you how you can construct it. But the thing I want to show you is that for choosing this sign, you should be careful that your string doesn't include dollar inside it. I mean, the sign that you will use here, it shouldn't be inside your string. Like when we talk about DNA level, we know that it contains 4 letters only. So you can use any other letters to say, for example, this one represents endpoint. Like, for example, instead of dollar, you can have AAB. Doesn't matter, they are just title, right? Just make sure that this letter, this character is not inside your string. Okay, let me show you how to construct a suffix tree in general, even for more complicated case, not just for 3 letters. Now, let's say I want to do it for this string, for 6 characters. So I know that at the end I should have 6 number of leaves. So the first edge can be XAB, XA dollar, the whole string itself. So maybe I can show you even here right away. So what we are saying is that at the beginning, let me show you here. Oh, what was the whole string? XAB, XA dollar. XAB, XA dollar. So I can have a edge for this one, and that's it. This is my first leaf. But this is the final version, and I want to show you how many changes I should apply in order to reach this one at the end. But first thing first, we are doing this. So for the previous example, let me also, maybe it's not bad I show you for the previous one as well, which is easy. So for the first one, we try to have AA dollar. It won't remain the same, as you know. We should apply some changes. Okay. So the first leaf so far was easy, but maybe we should apply some changes later. The second one can be ABXA dollar. It means that I eliminated the first letter. So for having the suffix tree and constructing it, I don't necessarily do the way that I did for suffixes. For suffixes, you remember, we started with dollar, then we will have A dollar, then XA dollar. But for constructing a suffix tree, it's better not to start from the last one to the end. It's better to eliminate the first letters. This is the best way. You will see why. So for the second one, I consider AB XA dollar, and I call this one for the time being my second node. Okay, but as you see later it will change. So for the third one, again, I will use the same method that I'm eliminated the letters. For example, for this one, I eliminated first. Let me show you all the letters: XB, XA, dollar. So first I eliminated this one, then I eliminate A. What I have now, BXA dollar, this one. So the third node will be BXA dollar. I wish it was that easy, but it's not. I will show you why. So now the next one we want to do is to eliminate B, and I will write it like this. But there will be a problem. What's the problem? We want to consider XA dollar as the next one, but it has character matches with XABXA dollar, because you see from the first leaf, this one, you have already X at the beginning of it. If I want to have a new edge starting with XA dollar, starting with another X, so it will be a contradiction to a property that we mentioned before. We cannot do that. So what can we do about it? So we can split the edge of the previous one that we already constructed from the common letters XA. So you see from this one, because they have XA in common. The first problem we noticed was the X's which are similar, and we noticed that the second letter also is in common. So maybe it's not a bad idea, so that I split my edge from the middle and consider this part as one and this part another one. So what I have now, XA. Now the rest of it I can consider this, and the other part I can include XA dollar. So you see the common part, you can split your edge from that. This is a good sign for you. Whenever you see the common letters like this, that's the part that you should split your edge. Now I can cover both of the suffix now. This one, which was the first edge at the initial point, now we could construct two edges out of it to include both of them. Let's continue and we will see. The same story for a dollar. So I eliminate this one. I want to construct this. I see I already have one root that which, for example, this one. This one, it includes A already. So if I want to consider a dollar, then I see they have common characters. So that's only one letter. You know, we don't have dollar right after. We have dollar later, it doesn't count. They should be together. So it shows me that this common one should be the place that I should split my edge. So from this part, I can both include this string that we mentioned before and this one. Now I have already my $8 suffix and also this one. This is the way we split them. And for the last one, this is just a dollar. And I don't have any problem with this one because none of the suffixes start with dollar again like the others. So for number 6 was pretty easy. So that's the way we constructed suffix tree. So let's do the same way for the simple one that we had before. So we had a dollar, and we want to do the same. So what we do, we start with the whole string instead of starting with dollar, like the way we did it for having all the suffixes just as substrings. But we want to construct suffix tree, which is another story. Okay, next thing to do is eliminate the first letter and consider $8. If I want to do that, there is a problem. Why is that? Because it starts with A, and I will have A here as well. So what to do? Split it from this part. So what should I have? I will have A. One of them goes to $8, and the other one. So we will have this one $8, and the other one I wanted to consider was just $8. So I will have this. Okay, so far I have 2 leaves. What about eliminated the second letter? I will have only $1. So that's it. So this is my suffix tree, which includes 3 suffixes. Whenever you want to check, you should make sure that the size of your string, here for example, is 3. So I should have for sure 3 leaves, as you can see here. So for these ones, please go through this slide again and again to remind yourself how to construct a suffix tree, because it's important for us. Now, let's say we want to find patterns using suffix trees. Let's say you know already how to construct it, and maybe you see it in a book right away, and you want to see whether manually you can see the patterns or not. Let's practice with these patterns. For example, for XA, how can I find it? From the beginning. All the time we said these prefixes should be, they should be prefix of the suffixes. It means that it starts with the root. So starting from here, right away I see XA. Okay, so we can say, yes, I can find such patterns in my strings. I don't care whether there are other ones here. As soon as you see the first one, you understand, yes, I can find it. So next pattern, AC. I start from the root and I see, no, I don't have AC here. But no, I have A. It's okay, I continue. Maybe later I will see it. So later I see, yes, I can see this one. So from the leaf number 5, I could find this pattern too. So this one I could find, this one I could find. What about XB? I start again from the root. Not this one, not this side. Again, from this side, I have XA, not XB. If I had, for example, other one, say X, maybe I could continue like A and I would find, but even from the beginning, I understood it doesn't exist. So you see, instead of going through the long string, by just looking at the suffix tree manually, you can even understand that we cannot find XB inside my string. So that shows how useful suffix trees can be. Like if you have very large string and your substring, for example, contains X, B, X, A, B, X, even for just 3 letters. Maybe in your large string, you never experience such substring. If I say find this pattern, then from the beginning, when you start from the root, you don't see this. And for example, in your root, you have only these options. For example, XA, and then, for example, A. It starts from these 2. And from the beginning, you understand that you cannot find this inside your large string. So yes, this can be very useful. What about next one? CB. I have C, but I don't have CB. So I continue with C until here. It doesn't continue. It doesn't have any other children. So no, I cannot find. XAC. Let's see. For the root I start, I have XA, no problem. I continue here. Not this one, but yes, I can find it here. So in the 4th leaf, I could find XAC. I could find this one with no problem. What about XAX? So I start from XA until here. The next letter should be X. Here it is C, here it is B. Again, I couldn't find it, so I couldn't find this one. So this is how we can find the pattern through a suffix tree, which is very useful. And that's why I'm telling you, if you are designing a database, instead of going through all of your string, assume that you are dealing with the genome. So it takes a long time to just linearly go through all the string and check one by one whether you can find the substring. You can save time and space by just constructing a suffix tree for your database. So the other thing we can talk about is related to suffix arrays and why they are necessary for us, and when I compare it with suffix trees, what's the advantage there and what are the disadvantages. So when we talked about suffixes, we mentioned that based on the size of the string, it has, for example, 8 of them. So from the beginning, I know I should have 8 suffixes. So assume that these are the suffixes. What we do in the suffix arrays is that we try to sort them alphabetically. So we can start with the character that we don't know about it inside our string. Sometimes they show it in the last one, doesn't matter. And then from A to Z, you can sort them out. So if you sort them like this, then it will be very easier sometimes to find your substring. Like when I say, does it contain BAX, for example? And by looking at it, you understand from A to C, there is no B here. So right away, you understand it doesn't contain BAX. Or for example, GA. Let me show here. GA. I will find G, but after that, there's no A. So this pattern can be fine, this pattern can't be fine. So these ones can be useful. So how do we organize them in our database? You can define this one as an array, and these are just the elements of your array. See, so you already know as computer engineers or programmers how to deal with that for sure. So easily you can define it as arrays, and you can define your elements as strings, and you can save it inside your arrays. So it's well organized. It can save time also. You don't need to go through other possibilities of your suffix trees like we had. Then right away you can find it. But the logic is basically the same, right? Because for checking the suffix trees, we start from the root and we check whether we will find, for example, the first letter or not. The logic is pretty much the same, but it can save time and space comparing to suffix trees. So that's the advantage of suffix arrays comparing to suffix trees. But suffix arrays are not suitable for an approximate substring. That's a big problem. It means that, for example, on Google, on a search engine, when you type something, maybe you have some mistype, then it will give you some similar results at the end. Not for suffix arrays, it should be exactly the same. If, for example, you define this big substring, and for example, by mistake or by any reason, maybe that's the way your substring defined anyway. Instead of this, you just define it by X. And so the suffix arrays won't give you any idea whether we had a substring which was very close to this one, but just for one letter, we couldn't find this pattern. So this is a big disadvantage of suffix arrays. And sometimes we have problem with it. But anyway, we should always keep it in our mind that it should be 100%. If it is 99% match, it doesn't show you. So Guys, it was the topic related to suffix trees and suffix arrays. For sure, we should practice more about constructing, especially suffix trees together. We will do it by giving you the next weekly assignment. We will practice it. As you know, we will have time. Just I'm not very strict about your answers about the weekly assignments. As long as you are tackling it, as long as you are studying it, it's good enough for me. But our ultimate aim is that we are getting ready for the midterm and final exam. That's what I'm expecting you guys to just week by week go with these assignments that I'm giving to you and try to read the book whenever necessary, whenever you think, for example, I couldn't solve it, maybe I need to read more. For example, for suffix trees, I don't suggest you guys to read other materials because sometimes it can be confusing. First, wait for our weekly assignment. Let's see if you can construct it. Then, after you submit your work, I will give you feedback, and specifically the week after it when we solve it in our online sessions. Because we have, for example, I have 400 students this semester. It's impossible for me to go through all your answers in detail and give you personal feedback like that. And that's why I will give you everything in details in the online session. But anyway, I go through your assignments briefly, and if there are major problems, I will give you feedback anyway, as much as the time lets me. But even if you receive 100, please make sure that you will go through the videos of the solutions very carefully, because I'm trying to prepare you for midterm and final. That's my main goal here. For assignments, we are practicing together, and don't worry about your mistakes in the assignments, okay? And try to submit it as soon as possible, so if there will be any feedback, for example, if you receive 50, then you will have time to make it 100 through the week. Okay, guys, if you have any questions, let me know. Otherwise, I will see you guys on Wednesday, and we will deal with the second assignment. We will go through it in details, and I will tell you how you can provide the answers to be considered perfect for our midterm and final.